for getting to this point. Today, we are joined by four esteemed panelists, Maithri Venkat, Mohamed Elkadragy, Mandy Chen, and Daniel Koch. I'll be introducing them. So Maithri has over 10 years of experience in leading self-development projects, performance assessments, and new product introduction for lithium-ion battery cells. She's the program director for Women in Batteries at Volta Foundation, where she champions and drives initiatives to support and elevate women in the battery industry. Next, we have Mohamed Elkadragy. Sorry, Mohamed, if I pronounced your last name wrong. I practiced a little bit this morning, but I'm not sure if I got it correctly.
No, it's
Mohamed,
perfect.
perfect. Thank you. Mohamed is a distinguished expert in battery and renewable energy storage with over 15 years of global experience spanning industrial leadership and applied R&D. So currently, Mohamed serves as a program manager in for battery and hydrogen fuel cell technologies at one of the world's leading automotive and e-mobility companies in Germany. Besides that experience in large-scale grid-connected BESS, CNI, and residential storage system, and PV and batteries in a top-level German world-leading company with global project exposure. So Mohamed has quite a large breadth of experience that he's had in the past. Next, we have Mandy Chen. Mandy Chen is the fundamental R&D manager at COSMX, responsible for material development and chemistry platform development. She leads the battery cell manufacturer's efforts on battery form factor and chemistry development before new product introduction, which is very pertinent for today's panel. Lastly, we have Daniel Koch, who is a senior manager of Electrified Powertrain high voltage core engineering at Ford Motor Company. That one's a mouthful, but it's also very important, where he leads efforts in advanced battery pack integration, safety engineering, and high voltage systems design. He brings deep expertise in aligning cell chemistry, form factor, and pack architecture to optimize energy density, performance, and manufacturability in next generation electric vehicles after 25 years at Ford. So today we'll be discussing the topic of EV form factor and chemistry. This is quite an important topic for the batteries in the EV space, as it determines all aspects of performance, of safety, of almost everything, warranty. So we'll start off the panel with a little bit of a broader question, focusing on trends in the industry. And I want to give this question to Maithri. So Maithri, currently battery cell design is splitting into two main trends. We have LFP cathode chemistries in prismatic formats, and we have NMC cathodes plus silicon anode blends in the cylindrical format. And so I'd love to hear from you, how do we get here, and why would chemistry and form factor be codependent?
Yeah, that's a great question. Actually, first of all, before starting, yeah, thanks, Michael, for having me in this panel. I'm super excited to give thoughts about this. So this question about like the codependence between chemistry and form factor is kind of rooted in the intrinsic material properties, safety requirements, the energy density needs, and also manufacturing considerations of like each chemistry. So for LFP in prismatic format, the driver has mainly been cost competitiveness, safety, and cycle life. So LFP's lower energy density makes it less sensitive to the packaging efficiency. And also the prismatic format allows higher volumetric utilization in pack designs, especially for applications where range can be traded for like durability and cost. And for the other chemistries, so you were mentioning the NMC with silicon blended anodes in cylindrical format. The focus is on achieving higher specific energy density and power for performance-oriented EVs. And one thing to note is that the cylindrical cells offer like excellent mechanical stability and have like high throughput manufacturing lines. So it's really advantageous for chemistries with high energy densities. So the current industry trends, it kind of reflects a codependence rooted in material science as well as manufacturing optimization, I would say. So each pairing is chosen to maximize the specific advantages of chemistry and form factor for targeted applications.
Fantastic, thank you. So from my understanding, LFP cathodes and prismatics, those are more for cost-conscious applications, and then for high performance, we're seeing this spread into NMC and cylindrical formats. Perfect, thank you. We'll have to open up the questions to our panelists. I have a couple of overarching questions I'd like to ask Maithri and Daniel. First one, what dimension of energy density do you see as the highest priority to optimize? Volumetric or gravimetric energy density? And what chemistry and form factor combination gets you the closest? Maithri, since you just spoke, Daniel, I'd love to hear your thoughts on this. Oh, if you want to unmute yourself first, we can hear you.
Is that better?
There we go. Thank you.
Okay, very good. Yeah, so thanks for the question, because I think it's an interesting one, an important one. So, as always, the answer is it depends. It depends on the application. And let me give you a couple of examples. You're probably familiar with the F-150 Lightning that we have as an EV product. That is an existing platform. In that existing platform, you have hard constraints when it comes to the volume that you can occupy in the vehicle and within the frames of the vehicle. So there, the volumetric and energy density typically is more important to deliver range and performance capability. If I take a different example, the Mach-E, for instance, the Ford Mustang Mach-E, there, effectively the vehicle was built around the battery pack, and some of you may have seen earlier this week that we're working on the introduction of this new Ford Universal Platform. Same approach there, where the vehicle will be built around the battery pack, and that just means, per definition, that things like crash safety, the whole vehicle architecture is set up such that there is more volume available for the battery pack. So that's where volumetric energy density may play a lesser role. And then there's a third type of application, commercial vehicles. And again, we have an example there with the Ford Transit, probably many of you are familiar with. So their payload is a big factor, right? So when we talk about payload, but maybe the dimensions of the vehicle and the architecture allows for the installation of a fairly large battery pack, it actually becomes more the energy density, so the specific energy, the gravimetric energy density that is important for those applications. Because for every kilogram of battery pack that I install in a vehicle, I need to give up some payload.
I really like that response and appreciate you contextualizing application and product requirements. I think that's quite important in the conversation. Mohamed, I'd love to hear your insights and thoughts on this question.
I actually totally agree with Daniel, especially the last comment about that each application has its own needs. For commercial vehicles, the payload is really, this is what you use in the business at the end. So there is no one size fits all, but what I have seen along the periods of the battery industry, like 10 years ago or 12 years ago, we were questioning even if cylindrical cells will still exist in the market, because pouch cells were dominant in the R&D. And now we see cylindrical cells as a backbone of the battery industry. So there are really, the first comment I have is that there are really changing thoughts which we have been going through during the last 10 years. And it will keep like this, at least from my perspective, for the next 5 years, because we are still figuring out the way of mixing the right cell format with the right cell chemistry. So I don't think that we are mature enough now to answer the question, but we really could see that nowadays people are looking for example, a truck or a bus is not a big car. It's a totally different application. And really, I have seen this in practice, and understanding the application will get you to the point that, okay, maybe prismatic cells are more preferable in large vehicles. But why they are like this? If they do not get big enough, then cylindrical cells would be more preferable. So there is the first point which I want to raise is that still we are facing changes into mixing the right format with the right cell chemistry. But nowadays we do see that pouch cells does not play a big role, especially in automotive, like it was before. It's mainly cylindrical and prismatic. And the third point which I want to make is that large prismatics as well has the biggest benefit of using less cells. So we do see a trend into going more in large formats, whether it's cylindrical or prismatic. So I I think that it will keep like this, but understanding the application very well is gives at the end the answer of using the right mix at the end. We all know this, but we don't have really. You cannot set up a matrix and say, okay, if you have this and that, then take LFP in 4680, and there you are okay with your user application. This is the point I want to raise now. So it's a very engineering and very cost-driven and as well effort-driven process to select the right cell for your application. And there is no one size fits all. This is the main comment I want to make.
Absolutely. It's also manufacturing and defect driven too. With yields, I think that's also a big portion of the conversation. And Maithri, I'd love to hear your thoughts. I know you gave us an intro on form factors and chemistry, but perhaps for this question, I'd love to hear what you have to think.
Yeah, I think you really can't talk about volumetric energy density and gravimetric energy. Like, you can't talk about one without the other. They just simply constrain the system in different ways. Because, like, in case of volumetric energy density, we need to think about like how much you can fit in like a fixed physical space of the pack, right? So in a lot of the cases, the skateboard chassis, it kind of defines the length, width, and height of early architecture. So if you run out of space, there's kind of no way to like add more volume without redesigning like the entire vehicle platform. So that's important. And for gravimetric energy density, like every extra kilogram that's carried for the lifetime of the vehicle, it affects the acceleration and efficiency. So even in like mainstream passenger EVs, like improving watt per kg can allow for better range without oversizing the battery. So one thing I would say is like if you wanted to get to like maximizing both these metrics, like using some of the high nickel NMC cathodes or NCA cathodes combined with the silicon blended graphite anodes, it can come the closest to maximizing both of these energy densities, both volumetric and gravimetric. So that's also because this chemistry combination has like higher intrinsic material level density from chemistry, and so the high nickel NMC pushes the watt per kg and watt per liter up, and the silicon blends kind of raise the anode capacity beyond the graphite's limits. And we should also think about the mechanical and dimensional stability from the cylindrical format because it also is important to think about maintaining uniform electrode pressure, like thereby accommodating the silicon expansion and resisting the deformation over cycling.
Fantastic. Thank you. My next question for all of our panelists, because I think everyone will have a different answer. What single technology related to cell form factor or chemistry will have an outsized impact on e-mobility in the next 5 years and why? Daniel, I'd love to hear your thoughts first on this one.
Okay, I think I'm going to give a non-cell answer, if that's okay. Maybe I'll leave the cell for other people. So, but we talked a little bit about the form factors already, right? And if you look at the prismatic and cylindrical cells, they come with the advantage that they have a structural can, and that structural can transmit forces. It's not just to retain the jelly balls inside of the can, but it can also transmit forces. So if you build on that, as an industry, what we're trying to do, we try to democratize EVs, right? And it just means that we need to focus very hard yes on quality, yes on safety, but most and for all on cost, right? To get it into as many customers' hands as possible. So as you start to peel away the non-cell cost of a battery pack, automatically you start thinking about, well, can I make use of that structural capability of the actual cell can? And there you will find that the way how you retain a cell inside of the vehicle under all the road load conditions, vibration, thermal, etc. Very quickly you come to the conclusion that both for prismatic and cylindrical cells, you want to use some advanced 2K adhesives. So adhesives, I think, and again, 2K adhesives are not typical used in the automotive industry for body and white, so it's a new territory. 2K adhesives, potting foams, etc., to retain the cells and to bond effectively top cover and the bottom of the tray of a battery pack through the cell structure. I think is really an important area to work on going forward.
Gotcha. I think it builds on your previous comment of building around the cell and using it as a component instead of an addition into the framework.
Yeah, cell to pack, right? Cell to structure. Those are the terminologies that we use for that. Yeah.
Yes. Cell to chassis, cell to car. We'll see how far we can get. Maithri, let's go for you next.
So, like, I just want to start off with saying that, like, next 5 years is like not too far away. So, also, like, one thing, like, you brought up a poll earlier in the battery forum, Michael. So, this kind of relates to that also. It's very hard to pick one technology, but if I had to pick one, like, more on the immediate scale, I'd say the integration of like higher silicon anodes into high energy chemistry at production scale. So that's super important to note here. And so we're obviously already seeing like an incremental use of silicon and graphite blends today. But moving towards higher loadings while managing swelling, first cycle loss, and cycle life, this has the potential to deliver like huge percentage gains in both gravimetric and volumetric energy density at the cell level. So when this is paired with form factors, so those gains can transition it into like longer range, and which means like fewer modules per pack and also more interior space if you think about it, like for the same range target. And the reason it's also so impactful is that silicon's higher specific capacity doesn't just extend range, it creates headroom in the pack design. So this headroom can be traded for like smaller packs, like reducing cost and weight, or faster charging, or improving like performance margin. And one thing we should also keep in mind is the silicon integration should leverage a lot of the existing manufacturing infrastructure. That's super important. So that way it can be scaled faster than like a new wholesale chemistry change like solid state or something. And so it's not just a lab win. They're more of a like a near-term manufacturing lever that we can turn without waiting for like an entire decade for like a new chemistry to mature.
Absolutely. And from my understanding, because silicon is also just smaller of a material compared to graphite per energy density, it creates a thinner electrode. That's where a lot of the performance gains come from, is just having those thinner electrodes. Mohamed, for your response, love to hear what technology will have an outsized impact on the mobility space.
Well, I would say this is my personal opinion that 5 years, if we look at 5 years horizon, it's basically nothing in terms of automotive. So really, to get something in serial production, if we have a technology today, we need 3 to 5 years to get it into good serial production that we can use, whether in stationary storage or in automotive. So this is the first point, that if we look in horizon of 5 years, it means that the technology should be 100% ready today. This is my perspective. And the first point. The second point is that if we look at the technologies which are ready today, it's clearly that LFP is ready today. And NMC is ready today, so they are competing. And this is what we focus on for the next 5 years. But still, there is a potential for blends, LMFP, for example, because it's not a totally new technology. It has its own challenges, which people are working on. So this is something as well which could be into realization in at least within 5 years horizon in terms of LMFP. But if we look at solid state, I believe it will be not a potential in the next 5 years, because really we need to solve everything related to it from today's perspective to have it in serial production. I mean, if we look at like even lithium sulfur is not ready as well as a technology to be used. I guess from today's perspective, it's very interesting to look at sodium-ion batteries, but the main challenge is really I'm not afraid of sodium-ion. This is my own perspective in terms of cost. The cost will go down, but in terms of gravimetric energy density, especially. So this is the main barrier, which really it's a game changer. If we can solve this, the energy density of sodium ion within the next 5 years, and this is big companies like ATL are working on this and others, this will be the main competitor to LFP and LMFP. So those are really the core technologies which I do see. This is very industrial, not a research. It's very industrial perspective. But from research perspective, of course, 5 years can means a lot in terms of adding more silicon to the anode and so on, and focusing on new technologies.
Great. Mohamed, I have a follow-up question there. So CATL in their battery day this past year has revealed their new sodium-ion chemistry and platform. They've reached about 175 watt-hours per kg, as they claim. Is this enough for the gravimetric energy density for what you're referring to?
It's not. It has to get to the same numbers which we have for LFP today to be competitive. So it's still not enough. However, for stationary storage applications, it's more than enough. So there you don't have really the rush about having a gravimetric and volumetric energy density into certain limits, and that's why it's a very, very promising technology. Because once you solve this issue, which can be solved with even, not easily, but as mentioned before, even on non-cell level into the integration level. But there you cannot even have very high savings that will let it jump like 10-20% more. So on the cell level, it has to get to at least the same range which we have from LFP today, and then really it will be very dominant and promising.
Gotcha. Thanks for that answer. We'll be moving into some topic-related questions and specific questions for each panelist. And of course, if the other panelists like to hop in and chime in on adding into it, please do. Daniel, on the question of chemistry, I know that you're more on the high voltage pack side, but one of the elephants in the room is really Ford's announcement with LMR. I think a lot of people are quite interested in hearing more about this chemistry. So can you explain a little bit more why Ford has chosen this horse to bet on, and how might your team in particular approach integrating this into a pack later down the line?
Yeah, thanks for that. So we've announced that we're working on LMR. We think we have a couple of good pieces of progress made there in the development, in the formation process, and in general in the way how we want to apply LMR into our potentially existing and new vehicle platforms. One of the LMR, lithium manganese rich, big advantage is obviously the abundance of the materials. It can provide from a supply chain perspective interesting opportunities in the various regions, but also in North America, where, for instance, LFP supply chain is still being set up. We do have an LFP plant that you may be aware of here in Michigan, that we're in the process of commissioning and launching. But LMR has some good opportunities there to become almost a drop-in solution for applications that we have with NCM in let's say, in the pipeline today. So lower cost, LMR comes with the advantage of having a slightly higher, what we call trigger temperature, so more safe technology. That also means that not just from a cell perspective, we can come down in the cost, but also on the non-cell side. So think about thermal barriers, advanced materials that we need to use to maintain the heat that is being released in case of a thermal runaway of a cell. There LMR has some good opportunities. So the combination of those, including the fact that we can use it as a fairly drop-in type of solution, and are able to work with our development partners on progressing that, really makes an interesting next generation chemistry for us that we hope to bring into production before the end of this decade.
Great. I appreciate that answer. You touched on a couple of things, especially for safety. I wanted to ask this question to Maithri. Maithri, you're focused quite a lot on cell in your current work. From your perspective, do you see a limit in cell energy density before the design struggles to pass safety requirements? Daniel just mentioned the trigger point for LMR is a little bit higher than other chemistries. And generally, if you have more energy dense cells, they have more energy to release. Do you consider a cell's safety profile affected more by its energy density or choice of chemistry or form factor? Like, what are your thoughts on this?
Sure. So there's no like specific hard like volumetric energy density limit where like the cells can suddenly fail safety test, but you're right. Like as the watt per liter increases, the thermal and mechanical margins kind of shrink. So at higher energy densities, like any internal faults, like localized shorts, it can produce more heat in the same small space. And also, you need to remember that heat has less surface area to dissipate. So that's why the higher watt per liter cells tend to show larger temperature increase or higher peak pressures and also more aggressive venting in abuse cases. So I would say like chemistry is like one of the baseline driver of this risk. So LFP, for example, releases little oxygen and has higher thermal stability. So while high nickel NMC or NCA can release significant oxygen, thereby accelerating thermal runaway. So the volumetric energy density can act as a multiplier. So the same chemistry at a higher watt per liter will be harder to cool, harder to contain, if you think about it. So one thing I want to point out is that we don't talk about enough is the local energy density and variability. So a cell that has like a perfectly uniform loading, like the electrode loading at 800 watt per liter can be safe, but a local area of like over thick coating or like poor wetting, it can create like a high energy hotspot that makes the cell behave twice as dense in that area. So that's why we need to think about like while maximizing energy density, we also need to think about tighter manufacturing tolerances, better separators, and more active thermal propagation barriers.
Fantastic. Thank you. Thank you for that response. And just for everyone's awareness, we had Mandy Chen on our panel. I think she's having some technical difficulties today, so we're going to be focusing a little more on Maithri, Daniel's, and Mohamed's responses. A lot of really interesting things already, so I think we'll have plenty to talk about. Mohamed, I want to ask you, building on Maithri's response, do the considerations for heavy-duty applications change what is needed for chemistry and form factor, given like gravimetric energy density is more important, and maybe the safety profile, maybe requirements might be a little bit different there too. I want to get your thoughts on that space.
Yeah, I want to take the chance here to highlight as well a general problem which we have related to safety and aging, not only for heavy duty but for all the battery packs which we have today, is how sophisticated are our battery management systems to really control our safety, not on the cell level. Let's assume that we are using the most safest cells which we have nowadays. The problem is that the sophistication of the BMS as well, to understand the different cells or thousands of cells connected together on a pack level, and to make them behave in the comfort zone that they have, to really not abuse their aging or safety limits. We are, from my perspective, a bit far away from what we need because of the limitations of how we can really estimate basic things like the state of charge of each cell. It's a dilemma by itself. So even for heavy duty or for other applications, the BMS is a bottleneck that we need to work on as well and solve, because I think we focus on cell level a lot and uh, forget that we have as well a lot of work to do on pack level and batch management system, which can help us even with the limits of technology which we have a day on cell level. This is one point which I want to raise, and especially in BMS and into how we really model our cell behavior over their lifetime. And that's why we see a lot of solutions with using cloud BMSs, where you have computational power, but even it's not only the power of computing, which is the limit, it's how to model everything which happens inside the battery itself. This is a huge thing which affects really the safety behavior of your pack over its lifetime. And discussing about heavy duty, where you have like the vehicle is on the road like 85-90% of the time. It's not as a commercial vehicle, which is really parking. This is very challenging as well because you have really the packs are really used in an electrical in a commercial vehicles, and as well the exposure to that you are gaining money by the payload which you have. That's why really the gravimetric energy density plays a huge role here, because as mentioned before, each 1 kilogram you save, you can put it as a payload. So you have a challenge here that your pack is really used in the application. The application is very harsh to be considered in different, even used in very hot climate or very cold climates as well. And on top of this, you need to have savings on the payload or the gravimetric energy density. But the positive thing, you have a bit of space as well, and as well you have a good understanding of the um, history, or how those type of vehicles are used before, so you can really have a good understanding of the how they're gonna be used, even if they are electrically driven, which can be main design factor into your battery pack. But still, using it in a stationary storage or in a commercial EV, a battery BMS still has its very high limitations to enable us to use the full capacity of safety or the full capacity of what we have today, even on cell level safety, like LFP, for example.
Gotcha. I love that you touched on degradation. That's quite an important topic for determining what technologies and what engineering tools to use in creating EV packs. Maithri, you have a lot of experience and have a lot of expertise on cell variability and how that impacts metrics, NPI metrics, in cell qualification. What aspect of cell-to-cell variability is not really talked enough about in our industry?
So I think one aspect of cell-to-cell variability that's not really spoken about is how it can interact with like pack level lifetime and control strategies over time. This kind of also tags along to what Mohammed was mentioning earlier about degradation. So variability does cause uneven charge discharge of cells. So cells with like different capacity can reach their lower and upper control voltage limits, especially at different times due to capacity mismatch. So this does have an impact on performance. So the weakest cell would dictate like the pack cutoff voltage during discharge, and So thereby this effectively limits the usable energy in spite of potential in other cells. So cell to cell variability during aging is needs to be considered. It's not just the initial capacity. So there is accelerated degradation in packs with like higher variability. And then there's also the case of like uneven stresses. So because of these capacity or resistance mismatches, it can cause these weaker cells to experience higher thermal, voltage, and current-based stresses, and thereby you have faster degradation. And this also sort of creates a cascading effect where the weaker cells degrade even faster. So thereby the variability just widens it becomes much larger over time, even compared to beginning of life metrics. So the industry is definitely getting better at tracking initial production cell variability, but we also need to pay more attention to predicting and managing how variability evolves over real world aging scenarios.
Absolutely. And a lot of it also comes down to not only the cell, but also the integration. Daniel, as one of the closing questions is that we're running a little short on time. How does pack architecture impact the tolerance of specs for cell performance variability, something that Maithri just mentioned? And what are the critical factors to consider when designing like a 2P cell or a 20P cell, a pack?
Yeah, and so the way how I think about this is actually that whether I have a single cell or I have two cells or more cells in parallel, it's just the way how I've put it into a can, right, or into a pouch or into an enclosure. So one of the things that we see there is if you have smaller cells, let's talk about the cylindrical cells, for instance, lower amp hour, something like 30 amp hours, for instance. If I build up a pack of fairly large pack, 100 kilowatt hours, I can get into the 5P, 6P type of region. If I do that, it gives me some flexibility somewhere down the line of product development over the, let's say, 2 or 3 years or longer that you're working on a product, to match more accurately the energy needs of the product, if you want to fine tune that energy. So if you find, for instance, that your vehicle engineering colleagues have made great progress on aerodynamics, and all of a sudden for a given target vehicle range, electric range, I now need less energy, maybe I can talk about taking one parallel string out of the equation. If on the other hand, if I have very large, let's call it prismatic, high amp hour 1P type of battery packs, now taking energy out is a little bit more difficult, because now I need to do that in the series configuration, and thereby I'm going to be impacting the voltage and all the modules in my vehicle. High voltage modules and all my e-drive systems have been locked in when it comes to that voltage level. So smaller steps are possible when you have a large number of smaller cells in parallel. Bigger steps is what you're faced with if you have a 1P type of configuration. But a 1P type of configuration is pretty good when it comes to the overall cost. Bigger cells typically means lower cost for the cell and less cell-to-cell interconnects, etc. So it's a fine balance there, and there's no single answer to this question.
Awesome. Thanks for the contextualizing from cell to pack. I think oftentimes, especially as battery engineers, we tend to get too focused on one or the other. So I'm glad we have a good representation on this panel. We're running a little bit short on time. So I want to close out with just a very quick question. Let's have just like a lightning round for everybody. So maybe one sentence or less. Looking ahead a decade, what single success metric of your current work would you showcase to prove the industry success? Maithri?
So I would say, if it's just a single line, I would say it's about scaling innovations into reliable, repeatable manufacturing processes. I think that's super crucial, especially as we scale up as an industry.
That's it. Thank you. And Daniel?
For me, it's actually the CAE tool chain that we are setting up for design optimization early on in the process, where we can run through many variants of a battery pack and decide how we want to conceptualize that. And more we're making use of AI and machine learning tools for that. So that's where I think the big gains can be made still.
Awesome. Thank you. And Mohamed, close us out.
I believe it's how we did develop along the years, and we will develop into understanding how complex the battery product is. But on the other side, that the understanding of complexity really helps us to focus on the pain points. And as mentioned as well, the use of machine learning could help us in huge areas, but it will not solve the whole issue of what we have nowadays. So we will use a hybrid solutions as well. So I still have hope that in the next decade we will have a huge amount of understanding, especially for the complex issues related to aging and safety, with the help of machine learning.
Fantastic. Thank you so much. All right, everybody, please give a round of applause to our panelists, Maithri, Daniel, and Mohamed, for a great conversation. I think this is quite holistic across the value chain here.